In the world of cryptography, we're usually dealing with extremely large numbers. And that is one of the most powerful things about the RSA encryption algorithm that we will analyze soon, is that we're dealing with extremely large numbers, and the algorithm itself is not that sophisticated for how to encrypt and decrypt values. But the fact that we're dealing with large numbers makes it very hard to decrypt. And so there are a few modular arithmetic algorithms or reductions that we'll need to understand in order to utilize the RSA encryption algorithm as best as possible. So let's begin with a basic study of a couple of modular statements. So if it is the case that, for instance, that 9 is congruent to, we'll say, 6 mod 3, and we'll also say, and that's a true statement because 9 minus 6 is 3, and 3 divided by 3 is 1, and that's an integer. And we also will say that 7 is congruent to 16 mod 3. That's also a true statement. Why is it true? Because 7 minus 16 is negative 9, and negative 9 divided by 3 is negative 3, and negative 3 is an integer. So this is a true statement, again, because of the fact that 9 minus 6 divided by 3 is equal to 3 divided by 3, which is equal to 1, and 1 is an integer, and therefore that's a true statement. And it's also the case that 7 minus 16 divided by 3 is equal to negative 9 divided by 3, which is equal to negative 3, and negative 3 is an integer, so that's also a true statement. Now, one other thing that I could look at is, what if I added these two values here? That is 9 plus 7. If I added 9 plus 7, and I'm going to put a congruent sign here, if I also added 6 plus 16, then would it be true that 9 plus 7 is congruent to 6 plus 16 mod 3? Notice that the divisor here is the same as here. Well, 9 plus 7 is 16, and we want to know, is it the case that 16 is congruent to 22 mod 3? All right, well, the way I could check this is 16 minus 22 divided by 3 is equal to, that's going to be negative 6 divided by 3, which is equal to negative 2. And negative 2 is in fact an integer, and therefore this statement is true. Okay, so what this emphasizes is that if I have the same mod value, mod 3 in this case, that the congruence relations are summative. They can be added together. Now, one other cool thing to notice here is that if I take 9 times 17, I take 9 times, excuse me, not 17, but 9 times 7, which is just this times this, is that in fact congruent to 6 times 16 mod 3? So I'll write 6 times 16, put that in a box, just to emphasize that that's these two values. Is that congruent mod 3? Well, let's see, 9 times 7 is 63, and I'll put a question mark above here again to say, is that congruent to 6 times 16? Well, that's going to be 32, 64, 96 mod 3. Again, I'll put a question mark above here to say, is that true? And 63 minus 96, if I take that and try to divide that by 3, 63 minus 96 is negative 33. And if I divide negative 33 by 3, I get negative 11, and that is indeed an integer. So that leads us to a theorem that we're going to form, which is that if A is congruent to B mod M, and some other value, C, is congruent to D, but with the same divisor, M, then it is true that A plus C, that in other words, this value plus this value, is in fact congruent to this value plus this value, mod M. So as long as these divisors are the same, and that's important here, then the sum of the two values on the left is congruent to the sum of the two values on the right, mod whatever the divisor is. And similarly, I can say that A times C is congruent to B times D as long as both of these expressions have the same divisor, which is M. So if this divisor is the same here and here, then I can write these two statements. And that's very powerful because what it allows me to do is to combine two steps into one, or similarly, to take something like this and to break it up in two separate but smaller statements. Now you can appreciate this if we would, for example, try to write that, is it the case that, for example, 12 is that in fact congruent to 15 mod 3? 15 mod 3, which is a true statement because 12 minus 15 is negative 3, and negative 3 divided by 3 is equal to negative 1, and that's an integer. Also, we could say that 50 is congruent to 56 mod 3. And the reason that statement is true is because 50 minus 56 is negative 6, and negative 6 divided by 3 is negative 2, and negative 2 is an integer. But what this second property allows us to state is that if we wanted to find the congruence of two larger products, in fact, if we took 12 times 50, that is in fact congruent to 15 times 56 mod 3. So look at the statement. 12 times 50 is 600. 15 times 56 is 840 mod 3. Now this is not a horribly difficult problem to solve. I mean, 600 minus 840 is negative 240, and negative 240 divided by 3 is negative 80. But imagine that you're trying to find or establish whether this congruence is true. Well, as long as you can establish that these two congruences are true, then you know that the product of the left sides is congruent to the product of the right sides mod that same value. And this is where cryptography will become, this will become very important in cryptography, is as long as we have the same divisor, we could actually deal with very large numbers like this and break these numbers up into smaller factors and assess the truth of statements that way before we try to blow it up to something a lot larger. So these are actually, specifically this one here on the right, is a very, very useful property in cryptography because it deals with or leads to what we call modular exponentiation, where if we have an extremely large number this size, then we could actually break it up into something smaller to a power. And if we could break it up as something a lot smaller to a power, then we could break that up into multiple factors and deal with smaller statements like this one and this one, which a computer can do very quickly, as opposed to something where, you know, the order of these numbers is really, really large, then a computer may have a much harder time decrypting that. And so if you imagine a banking system where the bank has to process a lot of sign-ins every second, then breaking up large operations into smaller ones could actually lead to more efficient algorithms. And that's why this particular theorem is important. And so when we deal with RSA encryption, we'll see this starred relationship on the right to become one of the most prominent.